All right, this lecture is going to be looking at dating of rocks and understanding geologic time. So after you've completed this in your binder, you should be able to understand and be able to use the laws and principles to determine relative ages and sequences of geologic events, be able to apply the techniques of radiometric dating to determine the numerical age of a rock or mineral, and describe the geological time scale and list the proper sequence of the major events that have taken place since Earth's formation. And then recognize that Earth's history is detailed by the rocks, the fossils, and the structures that we see in the Earth's crust today. By being able to understand the structures, we can understand precisely what happened and when it happened in the past. So here's our geologic piece, that the Earth can change in the blink of an eye. When we look at natural hazards, that it's important to understand the energy in the event and the duration of time. That time and energy help describe what took place. But whether we define it as an event, which is a large amount of energy in a short amount of time, or an episode, a low amount of energy in a long duration of time, at the end of the day, whether it's an event or episode, the end result changes the Earth's surface in some way. And many of these are contained in Earth's rocks. So we use the rocks to determine what was taking place. An asteroid impact, a very high energy event, short amount of time. A volcano can be moderate to high energy, but a very short amount of time. A mega flood, once again another high energy, but a short amount of time. But we can talk about ice ages. Ice ages are low energy, a very large amount of time. And one could even say that a transgression regression of sea level change would be very low energy, a very large amount of time. So we're looking at it in terms of time. And then here are the principles we are going to be applying here. I want to make sure that we see that we can apply all of these at our next couple slides here. That unconformities also are features that tell us that, well, something was happening here. That rock was not being deposited. It was an erosional environment. And this here happens to be an angular unconformity, whereas this happens to be a disconformity. Disconformity, remember, sedimentary rocks, horizontal, over some erosive boundary over horizontally laying sedimentary rocks. And nonconformities here, we have horizontal sedimentary rocks. In this picture right here, this nonconformity, remember, these are all three are examples of unconformities, but non tells me that I have sedimentary rocks laid down within or over igneous and or metamorphic, and that's the key. Those are the differentiators. I want you to notice that even in this picture right here, in the sedimentary rock above the igneous metamorphic, you have inclusions. You have pieces of those rocks inside here. So moving on, when I start putting all of these features together, I get these rock strata sequences. Here I have a timeline here, and you can just follow with me. A is the oldest, then B, then D, then E. It then gets cross-cut by an igneous intrusion, letter C. H is a fault that disrupts A, B, D, E, and C in here. This igneous intrusion here was cut. This is a fault, also a cross-cutting relationship. And then I have this feature right here. This is an unconformity. And if I go back to it, let's see, I have horizontal sediment over horizontal sediment. That implies that I'm looking at a disconformity. So we're really putting it all together. And then the youngest layers are F and G. So we're starting to put them all together. And so now we're going to start adding the radiometric dating piece. That if I start looking at my ratios, right, the ratio of parent to daughter, I can then couple that with understanding the timeline of the event that took place, and I can put a very, very specific time to it. Remember, the decaying radioactive parent is going to be decreasing while the stable daughter is going to be increasing. And so over time I get these ratios simply by interpreting this graph. And so I put a timeline to it. So here's where I can put it all together. When I look at the geologic time scale, I can go and look at, okay, Precambrian. Precambrian is roughly 88% of all of Earth's history. That the Phanerozoic eon, right, we're talking eons here. The eons are your large groupings. That we're currently in the Phanerozoic eon. That the Precambrian is so vast it's subdivided into the Hadean, the Archean, and the Proterozoic, just based on what was taking place in geologic time. So the Phanerozoic is what gets the most it's got the most fame because this is where we are now. This is where life, we get multicellular organisms that kind of separate the timeline of the Precambrian to the Cambrian. And so we get multicellular material, right, fossils. And it took several billion years to get here. Some of the earliest fossils are found between 3.8 and 3.4 billion years ago. We're way back here in the Precambrian. And it took a few billion years for the single-celled organism to kind of master cellular processes. So we go from single-celled organisms that were primarily photosynthetic to now all of a sudden the change of the Precambrian into the Phanerozoic eon right? As we start moving into the Cambrian, we start seeing organisms with shells. We start getting more complex life. And that's the timeline, that's the window, that's the age of invertebrates here. And then as time continues to go on, I've got the Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, and Permian. These are all a part here of what I call the Paleozoic era, right? This is an era. So we have eons and we have eras. Eras are subdivisions. And I can even subdivide those into the periods. So we looked within the Paleozoic, or have the Cambrian, Ordovician, this sequence here. These are the periods. These are subdivisions. So I have the age of invertebrates. I have trilobites that lived here. I have some of the first fishes here. I start getting some of the first land plants. Notice that that marks the difference between Ordovician and Silurian. And the plants would have looked nothing like we think of today. We have fish that dominate. They're all over. They're starting to get more complex. Then we find our first insect fossils. We start getting just an evolutionary sequence, and we know this because we find the fossils. We can study what's going on. Here we have our age of amphibians. At the end here, with no more trilobites are found. So that's why trilobites are very nice index fossils, because it tells us they lived within this like 160 million year window. Maybe it's closer to 200, but trilobites only lived in this time frame. And then we start having dinosaurs. So this is where we start thinking, oh wow, dinosaurs, right? Jurassic Park. So we have the Triassic, Jurassic, Cretaceous. Those are the periods within the Mesozoic era. And this is the age of reptiles. And then we have this event that takes place 65 million years ago. And it's this asteroid that hit the Yucatan Peninsula. And after this point, we start labeling epochs. We have information that we have, well, let's just say we have a lot of kind of our mammalian history taking place in our more recent time. So within the past 65 million years, there's even a new division of an epoch, right? Periods are subdivided even further. And then we are up here at this line right here. We are currently in the Phanerozoic eon, the Quaternary period, the Holocene epoch. Oh, I skipped the Cenozoic era, sorry. So Phanerozoic eon, Cenozoic era, the Quaternary period, and the Holocene epoch. Like, that's our current time frame. So if I break down the geologic time again, so I'm looking at eons, eras, periods, and epochs. The eons, there have been 2 eons through geologic time, the Precambrian and the Phanerozoic. So, but the Precambrian is so vast, it's been divided in the Hadean. That was literally this bombardment phase of the Earth when it was organizing due to gravity. That was literally being blasted by asteroids, comets, just anything that large bodies that were gravitationally bound to the Earth began to collide with it. And that was really the building of Earth. Archean, we have the earliest life forms. We find that we don't know exactly what this primordial soup, it's kind of a theory, but we do start finding fossils, some of the oldest fossils, roughly 3.8 billion years ago. Then we have the Proterozoic. That's where our atmosphere begins changing, changing due to photosynthetic organisms that are just beginning to photosynthesize, take sunlight, and photosynthesis was taking place here, and oxygen's a byproduct, and it began to build up. And this took a long time. It took a couple billion years to get our atmosphere stable enough to be able to sustain complex multicellular life. Here I have eras. The Phanerozoic era is divided into Paleozoic. That's the ancient life. We have Mesozoic. This is consistent with your kind of dinosaur world. And then we have Cenozoic. That's the more modern world. Okay, here goes. Paleozoic, ancient time. Paleozoic here. Here we have, observe how life forms were evolving and changing. And this is evidence from studying from fossils and radiometrically dating the age of rock. So we have this kind of history here of the Paleozoic, ancient life. Well, they're very, very significant because this is where we get our fossil fuel region in the Carboniferous period during the Mississippian and Pennsylvanian. And this is just a time where plants were, well, let's just say they were these warm swamps, these shallow swamps were just, photosynthesis was cranking out these plants, and they were just being buried, and they were contained, and they eventually evolved from your process of coalification. As you go from plants into your peat, into lignite, into bituminous, and then over time anthracite coal. That this was all taking place. Most of our fossil fuels that we get on Earth are from this age of rocks. You find this age of rocks, you have the chance of having these fossil fuels. And lastly, Mesozoic. Oh, excuse me, not lastly, but dinosaurs ruled for about 180, roughly 200 million years. And what we have here is the Triassic, Jurassic, Cretaceous, and this is in the age of reptiles. That the age of dinosaurs ended about 65 million years ago. And we have evidence of this from this impact of the Yucatan Peninsula, and we have shocked quartz. It's an indicator. It tells us that something big happened. There's also a layer of iridium that is consistent with cosmic debris, but yet it's uncommon in the Earth's crust. So when you find it in one specific layer, consistent across the Earth, you know that something took place. But at the same time, there were flowering plants that were taking off, right? We have some of these flowering plants. And there were basalt flows that were changing the atmosphere, right? We have volcanism taking place. So maybe could all three of these features all had something to do with the end of the dinosaurs? I don't know. I wasn't around to see it. So, but that's kind of my theory. I think there's more than one, just that it might not have just been one event. Now, that would have been a really bad event, right? One bad day on Earth. But asteroids and comets and these craters, they're not uncommon on Earth. You know, think of this. All of these dots you see here, these are existing craters that we see today from impacts, impact craters. Remember, the Earth is only covered by 30% land. So that means we're looking at only 30% of all the cratering from impact craters that, in theory, if they hit the Earth, they're going to be randomly distributed. That means our oceans have taken a lot of bombardment too. So if we talk about this one right here, this is in your Yucatan Peninsula in Mexico. This is what it looks like. This is a topographic map that this is the northern peninsula here. And this is what it currently looks like here today. And these are maps of what it looks like underwater. And we have this nice iridium layer that is uncommon in the Earth's crust that is very reflective of the composition of the asteroid itself. And so where we find this iridium, we can say, yeah, something major happened, and it's consistent because it blanketed the entire Earth. And last but not least, now we look at the Cenozoic. And this is where humans evolved, within the age of mammals. And you know, when I look at the Cenozoic, we've got kind of this tertiary and quaternary. These are the periods that we're looking at, but it's been subdivided. We have a lot more history recently. It hasn't had time to be broken down and eroded. So just like our memories, when we create our own timelines, we remember a lot more took place today and yesterday and the day before than we do 3 years ago, 10 years ago, and 15 years ago. So you know, we've got more memory here, so it's kind of consistent with our own personal timelines. So I want you to consider a concept that when we look at dinosaurs ruled for 180 million years ago. And I would say, well, does that make them successful? Right? They're extinct now, or they've kind of evolved into what we see as birds today. But our humans, and our intelligence, are these determining factors for success? Civilization and humanity is about 10,000 years old. So we have the tools, though, today to destroy human life in many ways. Many ways. Are we successful? Is the current modern day of where we are in terms of intellect and with our brain capacities and being able to explore the Earth and our cosmos, does that make us successful? You know, does 1.8 million years of kind of hominid ancestry or evolution, does that make us successful? I don't know. Maybe you'll have the answer.